Hello, welcome you all to this session of the course Tools, Experiments and Techniques in Earth Science. Today we will discuss about the geological maps and mapping techniques. Geology is a branch of science that deals with the study of the earth and its resources. It gives the information about the earth history, trace the origin of the life on earth and allow us to understand the natural processes. But most importantly, it investigates the mineral resources as it controls the economic wealth of a country. We all know that the mineral of economic importance are recovered from the surface of the earth. But question arises, how? Therefore, in this particular lecture, we will discuss about the concept of geological mapping in view of the stages of mineral exploration. The sub-branches of geology like sedimentology, petrology, stratigraphy help us to understand earth history. Paleontology allows us to evaluate the origin of life on earth by accessing paleo-environmental and paleoclimatic conditions through fossils. Sub-branches like geomorphology, physical geology, structural geology help us to understand the natural processes that continuously reforming and reshaping the earth. Now, the first stage of exploration study is reconnaissance exploration. The purpose of reconnaissance exploration is necessary in order to adopt the precise exploration efforts for delineating mineral prospects targets. It requires a lot of background preparation at all scale of work, ranging from airborne geophysical survey and regional geochemistry to regional geology. Airborne geophysical surveys. Airborne geophysical surveys are very effective in very fast reconnaissance of large area. Such surveys are useful in inferring geological formations in covered and inaccessible terrains. Airborne gravity, magnetic and radioactivity detecting instruments are recently being used for the airborne surveys, which are very much useful for identifying lithology and structural discontinuities like fault or thrusted stone. It is also useful in mapping the structural favorable zones for the occurrences of the mineralization. This is the twin otter aircraft of Geological Survey of India used for airborne geophysical surveys. This is the instrumental setup of geophysical surveys. Now we come to the regional geochemical surveys. Now these days, mineral exploration is mainly aimed to locate the hidden deposits occurring beneath the soil. This technique is largely aimed to certain specific type of deposit, for example, iron ore deposits or massive sulfide deposits. However, this method is restricted to the search for relatively shallow targets. Application of remote sensing techniques. Remote sensing is a technique of obtaining information about an object without having a physical contact with it. Remote sensing techniques are widely used now these days for lithological discrimination. Remote sensing techniques include various mapping techniques that are carried out from airborne systems. Satellite photographs and imageries taken from spacecraft may be useful as an aid to regional mapping. Hyperspectral data are currently in great demands and are particularly useful in arid terrains as they help in inferring chemical variation in zone of hydrothermal alteration. Regional geological mapping. The national surveys like Geological Survey of India and state organization Directorate General of Mining publish regional geological maps of an area. Regional geological maps may be carried out on 1:50,000 scale and specialized thematic is carried out on 1:25,000 scale. The regional geological map give information about the regional lithostructural attributes of the area. Specialized thematic mapping used to prepare maps with special emphasis on search of particular mineral. Regional geological mapping. Later stages of mapping program are with specific objectives and are supposed to generate additional detail on litho sequence, structure and metallogenic aspects. Such mapping stages have some geochemical components and is demarcated in the reconnaissance permitted area. After reconnaissance stage, next stage is integration of regional data and delineation of mineral prospects. The available database on aerogeophysical, remote sensing and geological mapping are integrated for delineating a prospect. Based on geochemical signatures, the prospecting target are kept in sight before initiating exploration activities on the selected prospects. Such an exercise ultimately leads to preparation of prognostic maps and the less favorable areas are surrendered at this stage. The exploration activity henceforth shifted to the selected prospect through G4, G3, G2 and G1 stages. The third stage is mineral prospecting. Prospecting is a very important stage of exploration that includes surveying, detailed geological mapping, geochemical mapping, and finally detailed subsurface exploration. It includes surveying. Surveying deals with the techniques of detecting the relative position of point at, above, or below the surface of the earth. It is the device of measuring relative points at above or below the surface by making horizontal and vertical distances and angles. The objective of surveying is to prepare a contour map, a plan or section on a reduced scale as desired. It gives the true projection of the surveyed area of Earth's surface at a glance when the map is oriented. Surveying instrument. Surveying instruments include prismatic compass survey, plane table survey, theodolite surveys, total station surveys. Now these days, differential GPS are very commonly used for exploring a mineral prospect at G2 and G1 stage. Survey is to be done simultaneously with the geochemical and geological mapping. The geochemical mapping and geochemical surveys is almost entirely a dedicated methods employed for the search and establishing an ore deposit. The scale of work in a geochemical exploration is an important parameter which decide on the methodology, particularly based on grids, sample grid spacing as well as the medium of sampling. Depending upon the scale, the geochemical anomalies, which is the final output of the geochemical exploration, is graded. Locating the geochemical anomaly of a target base metal is the final output of a geochemical exploration. Such anomalies in a map are either decided by univariate statistics or by multivariate statistical analysis. Consider an example of detailed geochemical surveys. A copper-based metal bearing a primary mineralization shows a geochemical anomalies in the soil samples collected from the soil horizon occurring over the mineralized body. Finally, the detailed geological mapping has been taken up for subsurface exploration. The prospect by now has been well delineated and is ready for detailed geochemical mapping. The detailed mapping is carried out on 1:5000 or 1:2000 scale depending upon the intricacies of the prospect sequence. The objective of detailed geological mapping is to map small lithological units that are important from the detailed exploration point of view. The detailed mapping is generally accompanied by the detailed geochemical sampling along the boreholes, pitting and trenching for exposing the concealed litho contacts and or oxidized zones. Now we come to the concepts of geological mapping. The concepts of geological mapping can be studied under the following steps. It includes the general idea about the field geology, that means what is field geology, why study field geology, its importance and objective, how to learn and what to do in field geology, tools and equipments used in field geology. The second concept includes the phases of geological mapping that include planning and execution of the field work, parameters to consider in field, data recording, plotting data on working sheets or field map, and finally preparation and interpretation of the geological maps and cross sections. Field geology include collection of spatial and descriptive datasets like petrological data, structural data, or lithological data. These datasets are integrated in phase of field geology for preparation of geological maps, which ultimately help us to understand the geological setup and history of an area. Field study is the backbone of geological mapping. It includes selecting an area of interest, identifying geological aspects of the area to prepare a geological maps and report, and interpretation of geological maps. Field studies can be done for academic purposes like geological excursion for graduate, postgraduate students, research purposes, and mineral investigation and exploration purposes. Field study can be used in assessing the natural hazard for land use planning, disaster management, and impact assessment analysis. It can be used for academic purpose in studying petrology, stratigraphic correlation, and paleo-environmental reconstruction. It can also be used for mineral exploration as per the government mandate. So, what should we do in field geology, or what tasks we should follow during the geological surveys? First, we should orient our topo sheet or base map with respect to the north for site specifying localization, and then plan our field traverses accordingly for outcrop selection which is to be mapped. Once we reach to the outcrop, we should record our data like recording outcrop width, identifying rock types and its megascopic properties, measuring the oriented structures like strike, tip and azimuth, and drawing the sketches of geological structures. Then, if we want, we can collect some fresh structurally oriented rock samples in carefully numbered sample bags. Then we should plot our structural data and marking contacts on working sheet or topo sheets along with the strike of the marked bed using standard symbols. Finally, a geological map is prepared and cross-section should drawn to assess the various aspects of geology. While carrying out fieldwork, we should have precise equipments like base map, topo sheet to see the accessibility to the area, Brunton or clinometer compass for collection of structural data, handheld GPS for location, geological hammers for breaking samples, hand lens for seeing megascopic properties of the rock, sample bags and measuring tape for collection of the samples, diagonal scale, protractor, stereo nets and standard charts, field notebook and stationery for writing and data plotting, and a camera for collecting field photographs. During fieldwork, we should also careful about the enough food, water and potential risk for any mishap. And we also need to have obtained permission to visit the areas like private land, forested area which can be classified into protected or reserve forest. Now we briefly discussed about the instruments we use in field. Topo sheet. On our left, we have a base map topo sheet of 1:250,000 scale. Its segments of 15 minute by 15 minute is the topo sheet at 1:50,000 displayed at right. Now it shows marginal information like coordinates it covers, district it covers, surveying dates, state it covers, topo sheet number, conventional symbols and sign, its adjacent topo sheets number, scale and administrative index. Topo sheet also gives an information about major drainage system of the area including major river and tributaries, relative topography, general slope and outcrop pattern. Compass. Brunton or clinometer compass gives information about the direction by the orientation of magnetic needle. It measures the direction of trend of an outcrop in case of igneous rock, strike of bed in case of sedimentary rock, and cystosity of a foliated rock in case of metamorphic rocks. It also gives an information about the direction and amount of inclination of a particular rock sequence. The direction can be measured in full bearing and amount can be measured in clinometer scale. This is the photograph of Brunton compass. Brunton compass measures the orientation of geological planes with respect to the north, angle of dip of geological feature with respect to the horizontal. It can also be used in conjunction with topographic map for accurate determination of a particular location. GPS. GPS is a global positioning system, is a satellite-based navigation system and have three components: satellites in space, monitoring station on Earth, and GPS receiver. Now these days, it is widely used in geological mapping for finding location, tracking structure, measuring elevation, and storing sample points or data points. Geological hammer and hand lens. Geological hammer is used to collect fresh rock samples, and hand lens is used for detailed observation of all rock types and fossil material, such as rock type, color, texture, and identifiable mineral alteration. Sample bags are used to collect fresh rock samples. Measuring tape, notebook, and diagonal scale are used to measure and record data. Camera is used to collect field photographs. Stereo nets and standard chart. The stereographic projection is a methodology used in structural geology and engineering geology to analyze orientation of lines and planes with respect to each other. The stereo net is a type of standardized mapping system allow us to represent various angles in 3D space on a one-dimensional paper. Standard charts gives information about the grain size and it measures the diameter of individual grains of sediment or lithified particles in clastic rock. This helps geologists to infer the preliminary information regarding the depositional environment of a sedimentary rock. Now we will see what are the phases in geological mapping. For planning and execution of fieldwork, we first need to define our fieldwork objective. If my fieldwork objective is the assessment of mineral resources, then I should go and consider the lithology, structure and sample collection. If in case the objective of the field is biostratigraphic assessment of area, then we should analyze the microfossils in the rock formations. If my objective is earthquake monitoring, then we should go for the physical measurements. If it is the case of understanding of depositional environment, then I should analyze the facies of the sedimentary sequences. If my objective is to understand the climate change, then I should collect the samples from isotopic analysis. And if I have to assess the engineering property of a particular rock, then I should collect the structural attributes of a geological formation. After defining our objective, then we should need to define our scale of observation. In case of transit mapping, we can carry out geological mapping on topo sheet scale. As we have to measure the geological attributes, the detailed mapping should carry out on larger scale with the help of surveyor. It should be ranges from 1:1000 scale to 1:10,000 scale, as we have to measure geological attributes with the site specific location. After defining our scale of observation, we then need to decide our study area for geological studies and our way to approach the area. Then we have to decide our traverse line, like we should go across the general trend of the outcrop to get the maximum variation in geological attributes. Once we reach to our precise site for collection of geological data, we first need to orient our topo sheet or base map with respect to the north and then locate ourselves using GPS or traditional bearing-back-bearing methods. Bearing is a technique of getting the directional position of the object with respect to us, and back-bearing is the directional position of with respect to the object. For bearing-back-bearing purpose, we need to select first two known visible locations from our site. Then we should identify the same site on our topo sheet. Then we should plot the direction of bearing and back-bearing. The resulting intersection line is define our location on the topo sheet. Once we reach to our precise site for collection of geological data, we first need to orient our topo sheet or base map with respect to the north and then locate ourselves using GPS or traditional bearing-back-bearing method. Then we should plot the direction of bearing and back-bearing. The resulting intersection line is define our location on the topo sheet. Once we select the site and taken our location, we should observe and identify the geology by outcrop studies. We should measure the dimension and nature of the outcrop, that is, whether it is a continuous or discontinuous outcrop, it is a weathered outcrop, or it is a structural deformed, plain or bouldery outcrop. Then we should demarcate the litho-units, for example, whether a particular outcrop is of igneous rock or sedimentary rocks or metamorphic rocks. Identify the rock type. If the identified rock type is igneous, then what it could be? It could be a granite, it could be a basalt, gabbro or rhyolite. If it is sedimentary outcrop, then what it could be? It could be a sandstone or limestone, shale or chert. Or if it is a metamorphic outcrop, then we should define the lithology, whether it could be shale, phyllite, schist or gneiss. We should also identify the nature of the contact between different rock types, whether it is a sharp contact, for example, it occurs in the case of igneous rocks. It could be a gradational like in the sedimentary sequence. It could be irregular like in metamorphic sedimentary sequence, or it could be weathered like in igneous or sedimentary sequence. After accessing the information about the nature of contact of a particular outcrop, we should check the lateral continuity of the litho-unit. Like, is there any changes in the outcrop due to change in depositional condition, or is there any changes in the outcrop due to a structural disturbance because of deformation event. We also check for cross-cutting relationship between the rocks. If any cross-cutting relationship exists, then we can able to define the chronological relationship between the litho-units and able to do stratigraphic correlation. We should also check the evidence of deformation or displacement, like we should identify any shear zone, seismites or folding if exist. After the outcrop study, we should go for the individual litho-units or rock type study. If rock is igneous, then we should observe what type of rocks, it could be volcanic or plutonic, how it occur like in the form of batholith, dikes, sill, vein, xenolith. What is the color of a major mineral composition of a particular igneous rock? It could be mafic or felsic. what are the mineral species, what is the grain size, ranges from fine, medium to coarse, what is its texture, that is mutual relationship between the grains, and its relation with the associated rock. And we should also see if there is any structural attributes present within the igneous rocks like flow foliation, cumulative layering or chilled margin, etc. To understand the relation with associated rock, this field photograph shows the xenolith of a hornblende biotite granite within the coarse grain granite. If the rock is sedimentary, then we should observe what type of rock it is, like it is siliciclastic or mud rock or carbonate or conglomerate. What is the color of the rock and particular mineral species. We should also observe the grain size ranges from fine, medium to coarse. What is its textural maturity, whether the rock is class supported or metric supported, its relationship with other type of the rocks. We should also see the sedimentary structure if present, like cross bedding, laminations, ripple marks, etc. And we should also see if it contains any fossils. Sedimentary rocks can be analyzed to understand the sedimentary processes and depositional involved. When analyzing the sedimentary rock, we can also prepare the graphical logs of sedimentary section to understand the sedimentary processes and depositional involved. In case the rock is metamorphic, then we should observe what type of metamorphic rock it is. It is low to moderate or high grade metamorphic rock. What is the color of a rock and its mineral species. Metamorphic rocks are closely contemporary to the deformation events. Therefore, their texture can be analyzed in terms of foliated or non-foliated, pre, syn or post-tectonic porphyroblast. We should also see the reaction texture if exists in the metamorphic rocks like corona or pseudomorphs. The mineral composition of metamorphic rocks give us a clue about the metamorphic grade of a particular, what type of temperature and pressure condition it has gone through. Once we identify the rock type, we should go for the identification and measurement of structural attributes. After identification of bedding plane, we need to measure its three components, that is orientation direction of a plane in relation to north, direction of inclination, and dip magnitude. Dip magnitude is the maximum angle at which a bedding plane is inclined in relation to the horizontal. Strike and dips always has a perpendicular relationship with each other. On the left, it shows the image of relative position of Brunton compass with outcrop when measuring the strike of a dipping plane in azimuth scale. On right, it shows the image of relative position of Brunton compass with outcrop when measuring the amount of inclination of a dipping plane in clinometer scale. In real case scenario, strike line of an inclined plane is an imaginary line formed by the intersection of bedding or foliation plane with horizontal line. Its direction, if we see the photograph, the direction of the strike line is closest to the north-south. The direction in which the beds are inclined is toward the west, that is the dip direction, and how much degree at it is inclining toward the west is its dip amount. Likewise, other structural data such as plunge of a fold, lineation, foliation or cystosity, or cremulation can also be measured in the same way. Also, the true thickness of the inclined strata can be calculated using the formula d by sin theta, where d is the length of an outcrop exposed on the surface and theta is the amount of dip of an inclined strata. Now we comes to the sample collection part. Sample collection can be done simultaneously with the geological mapping. The type of sample collect is usually in accordance with the stage of geological mapping. For example, during regional geological mapping of 1:25,000 scale, usually random chip sample is good. The intensity of sampling increases with the upgradation of stages of geological mapping. That is, in large scale mapping, the chip sampling is replaced by channel sampling or core sampling. For petrological studies or thick section analysis, a fresh oriented rock samples of sufficient size of 10 cm by 5 cm is enough. For geochemical analysis, the powdered sample of 200 grams is enough to understand the molar percentage of oxides and trace elements in a rock. To understand the elements of economic importance in a rock, random unbiased chip samples are required for about 200 grams of powder. So far, Whatever data we have recorded, we should write in a sequential manner. This can include the date of fieldwork, location indicating the geographical coordinates or with reference to the landmark, on-location geological notes, structural data, sample details if collected, and field photograph or field sketch. Writing the field notes. So we should first of all write the date and the location of a particular area. Then we should note it down our particular observation regarding the lithological, structural attributes and its interpretation. The field notes has been also accompanied by the sketches, which used to infer the regional geological interpretation of a particular area. Then in the lab work part, we should have to plot our field data on working sheet or field map. This can be done with the conventional geological symbols and standardization of different type of rocks, whether it is igneous, sedimentary or metamorphic. Similarly, the contacts are plotted according to the conventional signs. Folds and faults can be also plotted in this way. In last and final stage of preparation of geological map, we need to plot our structural data parallel to the general strike of the outcrop. Then corresponding lithological contacts should be marked along the strike of the bed. Similar types of lithological data collected at different points should be considered under the same litho units. And finally, we need to interpret our geological map for further stage of mineral prospecting like borehole planning and for reserve calculation, etc. Therefore, in this picture, the area shows the two lithological units, phyllite forming the base and banded hematite quartzite at the top. Beds are moderately to steeply dipping towards south, and the rocks also show at least two phases of the deformation, and the area forms a part of a regional syncline. So this is Brenton compass. You open Brenton compass like this, and it is used to measure the direction of a particular outcrop, strike, tip direction and azimuth. It has the magnetic needle which always orient toward the geomagnetic north. This is topographical map prepared and drawn by Survey of India. It has shown the scale of 1:63,000